Hello everyone, I welcome you all to the next lecture of the JCE Connect series of online lectures. Today we will be discussing further the losses of prestress concrete, the problems of this topic. So let me come to the first example of the day. I have selected a small and easy example to start with. In this example, we are having a post-tensioned concrete beam which carries an initial stress of 1200 Newton per mm square. The slip at the jacking end is 8 mm. Modulus of elasticity of steel is given. We have to simply estimate the loss of stress in steel due to anchorage slip only. Two cases are given. First is the beam is of 10 meter length. In the second case, beam is of 50 meters length. Practically having a 50 meter beam is a difficult one, but still in the example it is the given data. So let's start with the example. Write down the given step. Here we have 8 mm as the slip which is given. So let's find the loss of stress due to anchorage slip. Here directly we can use the formula, that is Es into delta by L, which gives us the loss. In first case, let us substitute L is equal to 10 meters, and substituting the other values, we get a loss in stress equal to 168 Newton per mm square. Therefore, percentage loss is 168 divided by the originally applied initial stress, that is 1200, multiplied by 100. Hence, we get 14% loss for a beam length of 10 meters. So now in case 2, we are substituting the length as 50 meters, substituting the value of Es and length as 50, we get the answer as 33.6 Newton per mm square, which is the loss. Therefore, percentage loss will be 33.6 divided by initial stress, which is 1200, multiplied by 100. We get 2.8%. So from this example, it is very much clear that the loss of stress due to anchorage slip is significantly higher in shorter span beams as compared to the longer span beams. Okay, we saw here when the beam length was just 10 meters, the loss was up to 14%, 14%, whereas the beam length was increased to 50 meters, the loss is only 2.8%. So this example I have selected just to prove that the losses are very much higher for shorter length, whereas as the length increases, the loss due to slip decreases. Now again, this is a different example. Here we have a cylindrical tank of 50 mm external diameter, which is to be prestressed. We have prestressed circular water tanks, and this example is related to that. So here the diameter of the tank is 50 meters. So the high tensile wires of Young's modulus 210 kilonewton per mm square are used. Then the jacking is done at 4 points. Okay, 4 jacking arrangement are provided 90 degrees apart, means at if you have the circular element, say at each 90 degrees, okay, you have the jacking arrangement provided. That means the total circle is divided into 4 equal parts. Now this is the important thing in the given example. If the minimum stress in the wires immediately after tensioning is to be 500 Newton per mm square and coefficient of friction is 0.5, calculate maximum stress to be applied to the wires at the jack and the expected tension at the jack. Okay, so what we want to achieve is, we want a minimum stress in the wires immediately after tensioning to be 500. Minimum we should have 500. That is a given data, and it's a hint which we are going to use further in the solution. What is asked, or what we have to calculate is, maximum stress applied to the wires at the jacking end and expected tension at the jack. So it's a different example. Let's go through it. Now, so let P naught be the stress in the wires at the jacking end. Px is the stress in the wires at the far end, it is 90 degree apart. So it is basically based on your friction. No other things are given much. We have to concentrate on friction. Now Px is equal to P naught into e raised to minus mu alpha. So here plus kx term we are not considering, it's a circular element firstly. Then secondly, as we have the given angle, okay, and it is to be taken, hence the previous formula, the which one we used in the previous examples is not used. The main formula, which is e raised to minus mu into alpha, is used in this case as it is a circular element and we have a 90 degree angle. The angle is not small here, we have a well defined angle. Okay, so alpha is equal to 90 degrees, which is equal to pi by 2. Therefore, now Px is the stress in the wire at the farther end, which has to be 500, because initial stress which we got to achieve is 500. Hence, in place of Px, we can substitute 500 directly. So this is the most important thing from the given data which we have to take in this example, is equal to P naught into E value is 2.7183, which is a standard, raised to minus 0.5 into pi by 2. Here pi value they have taken it as 3.14. So solving we get P naught is equal to 1102 Newton per mm square. That means the initial stress in the wires at the jacking end has to be 1102 Newton per mm square. This is very important. Now here you need to understand 500 is not the initial stress, but from the example or the given data, 500 is the minimum stress in the wires immediately after tensioning. So now we have two stresses, that is the P naught and we have Px. So let us take the average stresses P naught plus Px divided by 2, which gives us 801. So now this stress we can use for your further calculations. Then next is length of the wire. Length of the wire we have to go, as it's a circular thing, we have to take into consideration the circumference. The formula for circumference is pi d, and as we have 4 jacking arrangements, we can multiply it by 0.25, or it is nothing but divided by 4. Pi d is the circumference, but jacking arrangements are 4 in number, hence it is pi d into 1 divided by 4. 1 divided by 4 is taken here as 0.25. That 1000 is taken to convert 50 meters into mm. Therefore, we get the length of the wire as 39250 mm. Now with this we need to find the extension at the jack, which is the other requirement of the example. Therefore, we have the formula. Okay, we have the formula as delta is equal to sigma into L by Es, where sigma is the average stress, which is 801. Length we have found out, that is 39,250 mm, divided by Es is 210. Now I think here 10 has come extra. Es 210 kilonewton means 210 into 10 raised to 3. Okay, not 10 raised to 4, you have to take 10 raised to 3. We get an extension as 149.7 mm. That means the jack will undergo an extension of 149.7 mm. So that is the second answer which we required. So this is a tricky example. If suddenly you come across this example in the exam, and you will get confused. Solution is hardly a single page, Only the thing is that we need to understand what is given data and what is asked. Here we wanted to find P naught, that is the stress in wires at the jacking end, and extension at the jacking end, so which we have found out. Let's move to the next example. Now this is a bit bigger example and I rate it as a tricky or a say difficult example. So let's concentrate. A post tension concrete beam with cable of 24 parallel wires, total area 800 mm square, is tensioned with 2 wires at a time. The cable with 0 eccentricity at the ends and 150 at the center is on a circular curve. The span of the beam is 10 meters and cross section is 200 by 450. The wires are to be stressed from one end to a value of F1 to overcome frictional loss and then released to a value of F2, so that immediately after anchoring an initial pre-stress of 840 Newton per mm square should be achieved. We need to compute F1 and F2. Further, we need to compute the design stresses in steel after all the losses are taken into consideration. So it's a tricky example. We need to understand first what is asked. In first step, we need to find F1 and F2, and in the second step it becomes a regular example where we have the initial stress. We have to take the given data into consideration and find the losses. Now what is F1? F1 is the stress from one end, okay, to overcome which loss? Frictional loss, and then released to a value of F2, so that we get an initial pre-stress of 840. Okay, so first we need to find F1 and F2. So remember, here initial stage of pre-tensioning and later stage of pre-tensioning both will come into account when we solve this example. Coefficient of friction, wave effect, anchorage, etc., everything is there in the given data. So let's move on to the solution. So a figure is drawn where we have shown the eccentricity, cross section is also shown. So for this type of jacking, the total change in slope is 2 times of 4E by L, that is your angle is 2 times of 4E by L. Substituting the values we get as 0.12. So here, as your alpha value, that is the total change in slope, is very small, we can use the modified formula for loss in friction. So in previous case we had an alpha value of 90 degrees, that is pi by 2, hence we use the first formula, that is e raised to. Here alpha value is just 0.12, hence we can use the modified formula directly. The formula says loss of pre-stress due to friction is P naught into bracket mu alpha plus K into X. All the values are given, but we don't know the initial P naught. Okay, hence keep it as it is, and we'll get the loss due to friction in terms of P naught, that is 0.102 P naught. This is the first step. Then loss due to slip is given as 1.25. Therefore, using the delta formula, the total loss due to slip we can find. So firstly, PL by A is equal to 1.25. Therefore, P, that is the pre-stressing force, is equal to 1.25 into 800 into 210 into 10 square divided by 10 meters, which is the length. So we get the P value as 21,000 Newton. Here 800 is the area, 210 is the value of ES. Therefore, loss due to slip is 21,000 divided by area, which is 800, which is equal to 26.2 Newton per mm square. So be careful here, 800 is the area of steel which we have taken into consideration, which is the given data. Next, if the initial stress after anchorage is 840, the stress at the far end, okay, so when the anchorage takes place, there is a loss of slip. So if we consider the loss, stress at the far end has to be more than that, because here we are trying to overcome that loss initially itself. Okay, we want the final stress remaining as 840. So applied has to take into consideration the loss due to slip at the far end. Therefore, the stress at the far end will be initial stress, which is 840, plus loss due to the slip, which is 26.2. Therefore, initial stress comes out as 866.2 Newton per mm square. Now, the stress at the jacking end, it has to take into consideration the losses, which include your anchorage loss, okay, as well as loss due to friction. Okay, so here F1 will be equal to 840, which is the initial stress, plus 26.2, okay, which gives you an answer of 866.2 plus 0.102 into F2. Now we have got the relation on the previous page, that is P0 is equal to 0.102. Okay, what relation we have got? Sorry, loss due to friction is equal to 0.102 into P0. At that time we did not know the value of P0. P0, it is nothing but your F2, okay, which is the stress at the far end, which will undergo frictional loss. Okay, so the most important thing here to understand is what is F2. F2 is the stress at the far end. F1 is the stress at the jacking end. The stress at the far end has to be such that it overcomes loss due to slip, whereas the stress at the jacking end should be such that it should overcome loss due to friction as well as loss due to slip. Hence, for a initial value of 840, when we are calculating at the far end, it becomes 840 plus loss due to slip only, whereas when we are calculating at the jacking end, it accounts for the loss of friction as well as loss due to slip. Hence, F1 will be equal to loss due to slip plus initial stress, which is 840. The answer is 866.2 plus 0.102 P0. P0 value is nothing but your F2. So stress at the jacking end we get as 954 Newton per mm square. That means you have to apply and stress of how much? 954. Once you are applying a stress of 954 at the jacking end, at the far end you will get a stress of 866.2, and it will undergo the losses due to slip as well as losses due to friction, and an effective stress of 840 remains in the wire to carry your loading. So this is a tricky example, whereas you can understand many things from it. It tells that always the stress at the jacking end will be more than the stress at the far end. The effective stress is the one which takes into account the losses. At the jacking end, losses such as slip and friction are taken into account, whereas when we go to the far end, the losses due to only slip are considered. So Here we got two answers, F1 and F2, both have to be greater than the initial required stress, which is 840. So here first part of the example gets over. Now in the second part of the example, we got to consider 840 as our initially applied stress, okay, as it is given in the data itself. So other F1 and F2 don't play a major role here, okay. We have to consider 840 as the initial stress which is there in the wires, and just go on solving as we have solved the other examples. So first step, if you want, you can start with loss due to shrinkage, which is 0.0002 into ES. We get a loss of 42. Loss due to relaxation is given as 3% of initial stress, that is 3 by 100 into 840. Then the total initial force is stress into area, that is 840 into 800, which we get as 672. Therefore, the stress in concrete at the level of steel at the center span is P by A, which is the area of concrete here, 200 into 450, plus P into E divided by I. Okay, so here E we get it as 150. So we get the initial stress, that is, initial stress, right? Fc is equal to sigma c as 17.41 Newton per mm square. Therefore, loss of stress, this is loss due to elasticity. Okay, loss due to elasticity is alpha E into sigma c. Alpha is the ratio of ES and EC, which is 6, into your initial stress is 17.41. We get an answer of 104.4. Therefore, the total losses after considering losses due to shrinkage, loss due to relaxation and loss due to elastic deformation comes as 42 plus 25.2 plus 171.6 Newton per mm square. 104.4 Newton per mm square, which is totally 171.6 Newton per mm square. Therefore, final stress will be 840 minus the losses, which we get it as 668.4 Newton per mm square. So what visually you are able to see on the screen currently is a simple problem with initial stress of 840, whereas the background was F1 and F2, which were the stresses which we needed to obtain to maintain an initial stress of 840. So now I'll give you all a hint. In exam, this is a question paper problem. In exam, if this sum comes and if you find difficulty in finding F1 and F2, you can directly solve the second part so that at least you get 50 to 60% of the marks, which is a straightforward one. So these three examples I hope you'll go through. They were a bit different examples. Hope you'll solve them. So let's conclude for today's class. Thank you.